So the title of this paper is DMAAUTH, a lightweight pointer integrity-based secure architecture to defeat DMA attacks. So I will start by introducing the motivation of the research. Then I will discuss the characterization of DMA behaviors. After that, we will explore the design and the implementation of DMAAUTH. Finally, I will present the evaluation results and conclude this talk. Okay, first let's take a look at DMA attacks. DMA, or direct memory access, is a mature technology that allows peripheral hardware to access the main memory directly without CPU involvement. So various ports enable DMA, including the early 5-wire port, the recent Thunderbolt port, and the ubiquitous PCIe port. However, this capability also allows peripherals to corrupt memory and potentially control the entire system. Various real-world attacks have exploited DMA vulnerabilities over decades. The traditional systems use an AUMMU to virtualize physical address, allowing user program to access only the mapped memory using virtual address. However, this does not restrict DMA access. The de facto defense against such attacks is IOMMU. It maps physical memory to an input-output virtual address and only permits DMA using the virtual address. So the IOMMU significantly enhances the memory security. However, like MMU, the IOMMU manages virtualization at the page granularity. So when a buffer is mapped, the entire frame gets mapped. This means that other kernel data or pointers residing in the same frame are directly exposed to the peripherals. So we call this spatial vulnerability. The IOMMU also uses an IOTLB to accelerate address translation. But the invalidation of the IOTLB is usually batched for acceptable performance. This creates a time window after a frame is unmapped, during which the mapping still resides in the IOTLB. It allows the peripheral to access the unmapped memory region. We call this as temporal vulnerability. We can see that IOMMU cannot effectively defeat elaborate DMA attacks that exploiting spatial and temporal vulnerabilities. It needs a solution with stronger spatial and temporal guarantees. In the meantime, it has to be transparent to existing hardware and corresponding drivers. It should also introduce small enough overhead in both throughput and CPU time. So to design an effective and transparent mechanism, we first characterize the DMA behavior of different devices. The results show that most DMAs do not use the start address of the buffer, but rather with the offset. We also found that the number of coexisting DMA buffers is usually very limited, typically just a few hundred. So we also discovered that the majority of buffers are not page-sized, leading to the potential spatial vulnerabilities. So based on these findings, we designed DMAAUTH, a hardware-software co-design mechanism. Pointer authentication is a mechanism in the ARM architecture. It calculates the signature based on the pointer and puts the signature on the unused high base of the pointer. Then the signature is checked when the dereference the pointer. DMAAUTH applies pointer authentication to the DMA pointers and keeps the key in the CPU. It allows the kernel to control the DMA pointers. It also stores the bounds of each mapped DMA buffer to perform fine-grained bound checking for every DMA transaction to prevent out-of-bound access. Here is the workflow. First, the kernel allocates an object containing an I/O buffer, but the other memory area should not be accessed by the DMA. Then the I/O buffer is mapped for the peripheral to get the corresponding DMA pointer. Then the kernel recalls the metadata of the mapped DMA buffer, like bounds and mapping identifier. It also assigns the DMA pointer with the corresponding metadata. Then the kernel stores the metadata, making it ready to be referenced during authentication. So after the pointer is assigned, it is sent to the peripheral to perform DMAs. When the peripherals launch DMAs using the assigned pointers, the hardware authenticator that we placed on the bus retrieves the metadata according to the pointer, and then perform bounds checking and pointer authentication. Only legitimate DMAs are performed. Otherwise, an interrupt is raised to tell the CPU that the device is malicious and should be turned offline. As discussed, DMAs usually involve an offset, referred to as pointer arithmetic. This conflicts with the traditional pointer authentication mechanisms. We introduce arithmetic-capable pointer authentication to solve this problem. So instead of assigning the entire pointer, the kernel determines the length of the high bits to be used in signature calculation. The signature is then generated using the high bits of the pointer, the metadata, and the key generated at boot time. This way, pointer arithmetic within the offset does not affect pointer authentication. Metadata is generated for each mapping and participates in the signing and authentication process. It includes read-write permission, the length of the offset, a random identifier, and the bound of the buffer. The metadata is stored in dedicated storage and indexed using the signature on the signed pointer. When the signed DMA pointer reaches the bus, the hardware authenticator uses the signature to retrieve the metadata. It then checks if the pointer is within a legal DMA buffer using the bounds and recalculates the signature to verify if the pointer has been forged by the peripheral. The identifier in the metadata is randomized after remapping and is write-only to prevent any leakage. By introducing DMAAUTH to the system, the spatial vulnerability is resolved by the byte-grained bound checking. The temporal vulnerability is resolved with the identifier. The identifier is re-randomized after each remapping. This will change the hash result of the authentication process that can immediately invalidate the outdated pointers. To implement DMAAUTH, we first create a PCIe-capable research framework based on the rocket chip generator. This SoC features a fully customizable connection between the PCIe bus and the DRAM, serving as a research framework for various hardware software co-designs. Based on this, we implemented a IOMMU baseline, achieving only a 5.8% throughput overhead and 5.6% CPU time overhead, comparable to commercial IOMMUs. Based on the framework, we implemented DMAAUTH on FPGA. As shown in this diagram, the Authenticator hardware is placed between the PCIe bus and the DRAM controller. It is controlled by the CPU via MMIO, which transfers the metadata to the hardware authenticator for every DMA mapping. The authenticator intercepts all data transfers from the PCIe bus and performs authentication before the transfer reaches the DRAM. The evaluation of a real network interface card and NVMe storage shows that DMAAUTH introduces only 1% throughput overhead and 1.8% CPU time overhead, much smaller than the overhead introduced by the IOMMU. Okay, let me conclude this talk. This work presents DMAAUTH a hardware-software co-design which defeats DMA attacks effectively and faster than IOMMU. It is also transparent to existing hardware and requires zero driver modification. We also propose arithmetic-capable pointer authentication, which supports pointer arithmetic while ensuring pointer integrity. We also implemented a PCIe-capable research framework, which is equipped with high-performance IOMMU. This framework provides a customizable research platform and baseline for future designs. Okay, thank you for listening. If you have questions, you can contact the author of this paper. Here is his email. Okay, thank you.